Hi everyone, this is Vice Interim presentation done by Connor, Emma, Mark, Sundar, Vivian, and Catherine. Hi everyone, there are two different types of bench vices being considered. One is heavy duty multi-purpose meant for professionals, the other one is lightweight portable meant for homeowners.
Here we have the CAD model for our vise, and this one is specifically for our primary users, and so everything is made out of some type of steel or iron, and the pads are made out of rubber. Here is the exploded view of our vise, and we can see all of the individual parts and all of the fasteners.
This is the fast diagram for our vise that we are redesigning. So our main function is to secure the item that it is holding, and that requires holding the item in place and tightening the grip so that it does not move. We would also like to increase the durability of the product while decreasing the weight. This slide shows our assembly sequence fishbones. Both fishbones have a common base plate and frame subassembly, whereas the difference is in the order in which the handle mount and handle gussets are installed in order to prioritize either locating parts more easily or having a more stable subassembly to handle.
We compared two possible assembly sequences. Sequence 2 performed slightly better overall, mainly because adding the handle brackets earlier gives better support and makes fastening the handle mount easier later on. Sequence 1 is a bit more intuitive for locating parts and allows earlier testing of subassemblies, but is more linear and less flexible. Sequence 2, on the other hand, allows for some parallel work. For example, the tightening rod subassembly can be prepared separately while the main body is still being built, which helps save time and improve efficiency. So while both sequences have advantages, Sequence 2 would be the more efficient and practical choice overall. This matrix shows how each part of our vise contributes to key design functions. The baseplate, frame, and gussets provide structure and prevent rotation. The threaded jaws and handle assembly generate clamping pressure, while the quick release enables fast adjustments. The sliding jaws, made of plastic, reduce weight while maintaining grip and pressure. Overall, this mapping ensures every component has a clear functional purpose in the design.
We made a quad chart that categorizes the components by function and cost. The high-cost, low-function items are prime targets for improvement. The high-cost, high-function components can be considered, but care must be taken not to degrade function.
Functional differentiation on our product family design, our customer group similarities are going to be to prevent rotation, prevent slipping, decrease gap, release quickly, and increase pressure, which are the primary functions of our vise. And then for the differences for the customer groups, it will be to decrease weight and increase durability depending on heavy duty or lightweight models.
Here is our lightweight vise, which will be used by our secondary customers. On the next slide, Sundar will explain more about the differences between our heavy duty and our lightweight vise.
Hi, there is a common assembly between the heavy duty and portable lightweight models. So the mounting plate, base frame, handle mount brackets, quick release switch, tightening rod will be common for both models, whereas the moving clamp plate spacer will be made in plastic for the lightweight model.
While both of our assembly sequences allow us to install our differentiating components at the very end, by switching the order of the gussets and the handle mount, we're able to increase stability of the frame during our assembly sequence.
For manual assembly, our original assembly total time is 295.5 seconds, and our assembly efficiency is 0.12. To improve manual assembly of the frame, we added a cutout to the mounting plate. This eases assembly by improving access to the bottom of the vise, reduces weight, but maintains stiffness. Combining the frame and mounting plate into one integrated casting eliminates the welding operation. Assembly time for this step was reduced from 90% from 40 seconds to 4. We also combined the moving clamp, spacer, and plate into one piece. This creates a 90-degree assembly angle on two sides. Assembly time for this step was reduced by 18% from 70.42 to 57.76 seconds. After these design changes, the new total assembly time dropped by 48.6 seconds. Assembly efficiency improved to 0.12, all with no impact to product function.
For this step, we applied design for automated assembly principles by reducing part count and eliminating fasteners. We combined the moving clamp and clamp pads into a single component and removed screws from the assembly. This simplification makes the process easier to automate, reduces handling time, and minimizes error. As a result, the assembly cost for this step was reduced by about 13.6%, dropping from $12.36 to $10.68. This slide shows the original automated assembly cost based on the initial assembly sequence. The total automated assembly cost was calculated to be about $12.36 per unit. At this stage, the crankshaft support still required manual assembly, so they were not included in the automated cost calculations. This breakdown established the baseline we used to evaluate the cost reductions from our design changes. This slide shows the updated automated assembly cost after applying our design for assembly changes, using DFA1 to reduce part count and DFA2 to reduce fastener count. Based on the new assembly sequence, the total automated assembly cost decreased by about 13.6%. Importantly, these cost savings were achieved with no functional changes to the subassembly or the overall product.
There are two key parts that are redesigned as part of this vise. So one is the moving clamp plate and spacer, which is combined into a single piece, and also the mounting plate and frame, which is also combined into a single die-cast part. The combined mounting plate and frame is the most critical part of the vise, as it prevents rotation and helps holding the part steady. This is based off of the function component mapping matrix, and also the critical dimensions along with the tolerance have been mentioned here too. Hi, as part of the DfM process, so mounting plate and frame is combined into one single piece for efficiency, and comparing the machining and die casting process for the Zamek alloy materials with considering the other parameters like shape, mass, and thickness. So it's the final recommendation for the DfM process is die casting. So the second key part as part of this design was moving clamp and spacers. So we combined them into one single piece. And as part of the manufacturing process, the aluminum alloy was considered, and we compared various parameters for machining and sheet metal working. And the final recommendation for this one was machining.
This is a table showing the change in cost before and after our chosen DfM modifications. The moving clamp plate and spacer were combined into one part. An increase in cost of about 56% was estimated due to milling the surface of the plate instead of having two separate plates. The mounting plate, frame, and fixed clamp were combined into one die-cast part. An estimated cost savings of 7% is seen by reducing the total number of dies and die-cast parts.
When doing the cost comparison of our DfM process on combining the moving clamp plate and spacer, we found that the manufacturing cost increased. This cost, however, does not take into account the time saved during the assembly process. The discrepancy between the hub's costs and the analytical cost is likely due to extreme extrapolation using a maximum of 200 parts on hubs against our 500,000 units annually. The product service system that we can provide is aftermarket parts availability to the customer. This provides incentives for both the customer and business while also lessening environmental impact. This service allows the customer to replace worn-out parts or switch configurations as needed, which reduces the cost of ownership while also providing incentive for return business. By reusing the base components, we are able to lessen the environmental impact of manufacturing. In our DFA process, we saw improvements by 10% or more in both our manual and automated assembly costs. We were able to do this through adjustments made during our DFM process to combine or completely remove parts of the assembly. Some critiques of our product is that the system itself may struggle to differentiate itself from other existing products in the space. A new approach that we could use to benefit us moving forward would be to identify materials that would satisfy both customer groups within a single variant.